Good morning, everybody. Let me start by joining other speakers and thanking the organizers for bringing us all here and putting together such a nice program. It's really nice. Never been to Jeju, been to Korea, but it's really nice to be here and to participate in all the discussions and hear all the interesting talks that we've heard already and we'll hear in the remaining days. So I want to start with what I want to discuss with you is the quantum field theory of vortex lattice. Rotated superfluids that's become there's significant motivation for this in the context of this conference of effective field theory beyond ordinary symmetries, but also there's a significant experimental motivation in the realization of cold atoms, particular bosons, and ability of experimentalists in the AMO community to rotate these condensates and create beautiful vortex lattices as they explore their excitations. What I'm going to discuss is directly based on very fruitful collaboration with Yi Xian and Ho Tad, both of whom are postdocs at MIT. But it's also work that has pretty long background, some that I participated in that's listed here, but more importantly, a really beautiful body of work by good fraction of our organizers, starting with Sergey, Dong, Song, and their collaborators. They've really done pioneering work in the subject that I've only been, what I'm going to discuss is featuring that work, and we've only had a small contribution beyond what they've done that I'm going to share with you. Okay, so part of the motivation is for this conference is effective field theories beyond with symmetries beyond conventional symmetries goes back to these interesting quantum liquids, new type of quantum liquid, not so new anymore, which exhibit quasi-particles with restricted mobility that has already been mentioned throughout the conference. And they sort of broadly divided between gapped type of systems and gapless ones. And much of what I'm going to focus on is going to involve these gapless gauge field theories, U1 type. And so these systems exhibit a variety of fascinating properties like, their claim to fame is this quasi-particles that have restricted mobility, which translates into not having deformable string operators in the theory, but also the one feature that's often not captured by, or is not captured by sort of a field theory description of this, and in that sense beyond sort of standard quantum field theory description is very strong lattice dependence. If one stays in the lattice, there's features that you can calculate for a lattice model which are not easily captured in the field theory description. And so in that sense, one can say this is beyond sort of standard QFT, and it's still kind of a subject of current research and debate. So simplest, and we've heard this throughout the talks yesterday, simplest way to incorporate this restricted mobility is through encoding higher multipole conservation beyond the sort of the monopole conservation that we're used to, and that comes in through a particular form of the spatial component of the current being a derivative of a higher index current object, as illustrated here. And we've heard about a number of physical systems that exhibit this kind of a higher multiple global symmetries, such as, for example, particles moving in a tilted potential, where that emergent higher multiple conservation emerges from actually energy conservation, as we've heard earlier yesterday. This kind of physics also emerges in a lowest Landau level, guiding center hydrodynamics, and as I will discuss in quantum vortex liquids. Sort of prototypical lattice model has no standard hopping, quadratic hopping, but has this density assisted hopping of, well, that's one way to think of it, and the other way to think of it is just the hopping of dipoles. And to my knowledge, sort of earliest, first work that I'm familiar with because I've co-authored it with Lee and Balent, goes back to the ancient times of 1996, when we were just fresh out of grad school, where we discovered, thinking about completely different problem, thinking about melting of vortex lattices, and going to a lowest Landau level limit, this model emerged and had these symmetries that we're now discussing, has these higher multiple symmetries. We didn't appreciate, this is long before any fracton physics or any of these higher multiple symmetry discussions, so we didn't phrase it that way. But and this is very simply emerges from, even if you just take a standard Ginzburg-Landau theory and look at the lowest Landau level, the quadratic term is just degenerate, so you stay within the lowest Landau level. Now you have degeneracy, so there's no hopping from the quadratic term, so all the physics is in interaction. And now if you take in the quartic term, and so now if you take the lowest Landau level limit, you notice that this kind of a leading terms organize themselves, and the leading term has this form. And this dipole symmetry or this dipole conservation emerges as a consequence of momentum conservation. So when you're not able to hop, you're only able to hop in this correlated way because a position, let's say, think of a Landau gauge, a position in the y direction corresponds to momentum in the x direction. So you're not able to hop a single particle in the y direction because you will violate momentum conservation in the x direction. And literally this thing just pops out. Again, our focus was completely different. We wanted to understand classical melting, so that's why we were looking at classical Ginzburg-Landau theory. But if you just elevate your coherent fields to creation annihilation operators, you literally get this model. And then what emerged eventually in one phase of the system is this kind of a continuum Lifshitz model with its dipole U1 conserving symmetry. And recently, of course, there's been much focus has been on this kind of a model. Okay, yeah. Well, I can speak loud and abandon the mic. It's kind of a little bit awkward holding the microphone. I feel like I'm dancing with the stars or something like this. Okay, so that's kind of as a background. There are even more fine-tuned symmetries, these foliated charge-conserving symmetries, or so-called subsystem symmetries, where on every row and every column of your lattice, density is conserved, or total charge density is conserved. And this, in the context of conventional spin liquids, this arises when one thinks about, rather than individual single particle hopping, one thinks about ring exchange like hopping, where there's this correlated hopping of this type, where you can visualize it as a process in which particles in this coordinated way move around the fundamental plaquette. So that's this model is you can think of it is a plaquette XY lattice model, and then the continuum, it reduces to a form of a Lifshitz model with a different combination of derivatives, higher order derivatives. And more generally, one can think of models where these are indices with some elastic constant, or with fourth rank elastic constant that describes this kind of a high derivative coupling or elasticity. And so this model, as was discussed by a number of people, but in particular Seiberg and Shao, has this subsystem U1 symmetry where there's independent U1 symmetries on every column and every row of the lattice. So that's another class of models that give you this restricted mobility. And of course, there's also dual versions of this. If you dualize these models, then you get more robust and gauge-like descriptions, systems that will be endowed with this restricted mobility of their quasi-particles. And one place where this is realized, as many of you are well aware at this point, is amazingly in something very mundane and very familiar, namely topological defects in the crystal, whose dual of standard elasticity, just a bunch of coupled harmonic oscillators, dualizes to this tensor gauge theory, symmetric tensor gauge theory, where topological defects here map onto fractons and dipoles, where dipoles act like line-ons. And there's the dictionary that has been already represented in talks yesterday, where, for example, momentum conservation maps onto the Faraday law, the Lorentz force or electric field acting on a dipole, force of the electric field on a dipole translates into familiar Peach-Kohler force, known in elasticity on the stress act. If you apply a stress to a crystal, then the dislocations feels a Peach-Kohler force on it from proportional to the stress. Similarly, the glide constraint, which I first studied with Cristina Marchetti, also in the classical context of vortex lines. So it's a three-dimensional superconductor where vortices now are lines. We were trying to understand melting of those line crystals, and I'll come back to that. And there, what emerged is this kind of a glide constraint where Jij is a current of dislocation current. So in general, it's a tensor. Ij tells you, one index tells you the direction of the dipole moment or a Burger's vector, and the other is the direction of motion in space. And then it acts like a source to the continuity equation and breaks the continuity equation for the vacancy interstitials. And that, in the gauge theory, translates into this kind of a Ampere's law, encoded in the Ampere's law. So it's the right-hand side of the Ampere's law. So it just encodes the fact that if you have a dislocation and it climbs, it's a source of vacancy interstitial. So it can climb if you have a current, but then you'll have to generate vacancy interstitials. So that again, we had no idea there's this beautiful physics and mathematics hiding behind this relation, but we sort of stumbled upon it thinking about melting of vortex line crystals and line liquids in the previous century. So it's kind of amazing that, in some sense, that many of the themes of this conference and things that I mentioned come together in a fairly simple and, one could say mundane rotated superfluid or vortex lattice of a rotated superfluid. But on the other hand, given this connection to defects in crystal, it's not so surprising because, first and foremost, rotated superfluid forms exhibits a vortex crystal. A vortex crystal is an elastic medium, so first and foremost it's a crystal. So much of the physics that I described so far in conventional crystals must also be part and parcel of this kind of a crystal. But there's more, and the more was uncovered, in fact, by many beautiful works by Son and Sergei and their collaborators. And that's what I want to discuss. Namely, these are not just particles. I mean, these are vortices, so they're just singularities in the flow. So they're coupled to the underlying flow and their underlying superfluidity. So there's something slightly non-trivial beyond just ordinary crystals that this system has. And that's really the little piece that goes beyond of what's described here. And, it's a non-trivial, qualitative, non-trivial piece. But, it's now well understood, and at least at the harmonic level, we understand it quite well. Again, thanks to the beautiful work of our organizers. So let me just take you through this. First, thinking about it classically, and in fact, original work goes back to the 50s. But with Dan Sheehy, we looked at this again in the context of sort of classical problem of vortices and rotated condensates. And there, a slightly non-trivial thing was you have a trap potential. And so we were actually trying to understand, the thing that really haunted me as a condensed matter physicist and who have thought a lot about vortices and superconductors is why vortex lattices appear so uniform. Why are these crystals so uniform, even though the density varying by 100% across the condensate because of the trap potential? And okay, so that's as an aside, but I'll just pose that as a question. If you want to know the answer, you could look over here, but it's sort of in the slide. But anyway, that's just as an aside, but it's sort of at a classical mean field level. You have this Ginsburg-Landau theory with a quadratic potential or some trapping potential. And once you rotate it, you get this chemical potential for angular momentum, if you wish, or going to rotated frame. And curiously, not surprisingly, this looks like A dot J, where J is the current of the particles coupled to a vector potential whose curl is a constant magnetic field. Is a constant pointing in this direction, equal to this omega, proportional to this omega. In fact, if you go to London limit of this theory, which means you just minimize the amplitude and ignore the gradients of the amplitude of psi, then what you get is some profile psi squared, which in mean field theory is just a rho s of this fluid. And then you get all the gradients are in the gradients of the phase. So this is the kinetic energy, and this is comes from this rotation. It's just the velocity or momentum of this superfluid, rotated superfluid, dotted into this vector potential A, whose curl, as I said, is the omega. And indeed, if you now, first thing you want to do is you want to study this instability. So when you rotate, what is the solution of this guy? And so you look at a single vortex solution. If you look at a single vortex solution, this is the energy of a single vortex cut off by the trap size. And then this is the energy coming from this Coriolis force. Notice this term always beats this term in thermodynamic limit, but if a finite R, there's actually a phase transition. Much like in type 2 superconductors, there's omega C1. Below omega C1, no vortices enter. But if you rotate larger than omega C1, then vortices enter, much like in a superconductor. And they enter in this continuous way. And in fact, you can see that in thermodynamic limit, this omega C1 goes to 0. Okay, but in the trap, it's really a finite rotation, and it just says that you need to rotate fast enough that you have a single quantum that the corresponding angular momentum to that rotation, namely omega times moment of inertia of the cloud, gives 1 unit of h bar up to this log. Okay, so that's really the criteria for the critical omega C1. And so then, the profile you get as you go up this curve and you increase omega above omega C1, you get this combination of these singularities. Grad theta is this sum of these 1 over r profiles, velocities. And then the thermodynamic limit, it becomes just a linear. If you sum these guys up, replace the sum by an integral, this just becomes a linear profile of a rigid body rotation. So omega velocity, which is this grad theta, goes as omega cross r. Okay, but in detail, it's different than that. As you can see in this red curve, it just has a envelope that's linear, and that's sort of the quantization of vortices. The fact that the superfluid cannot rotates in this quantized way, and that's actually from that. Again, going back to this aside, the density, vortex density, is actually, naively, you would say, in the simplest approximation where you replace a summation by an integral, is just proportional to omega. But in fact, there's a correction, and that correction goes as a Laplacian of a log of this rho s of r. So that's a correction to how non-uniform, correction to the purely, perfectly rigid body rotation that you get from the vortex quantization, the fact that it can't rotate as a classical fluid. So then you look at this thing and you identify, you look at the Coriolis force here, V cross omega, and you identify, you notice that that's the same thing as just bosons moving in this, it looks like a Lorentz force, where effective magnetic field is just 2m times omega. Then you identify boson current with the density. So here's the density, here's the current. And so now you can start begin to develop an effective field theory. So there's definitely a superfluid component, which is just a standard XY model, if you wish, in this Lagrangian representation. Here's just, you can think of it as a Bose-Hubbard model with the kinetic energy and some compressibility term. And then there's a vortex part, the vortex lattice part, which in Lagrangian coordinates, there's some reference state plus some displacement, which is what we call the phonons. And if you turn the crank and put that into the total energy, you're going to get some short-range interacting lattice elasticity, where this is the kinetic energy, and this is just the elastic energy with the symmetry of the lattice and the elastic constants are encoded as this fourth rank tensor, and Uij is the usual strain tensor, which in principle is nonlinear, but all the calculations that one can do these duality manipulations really focus on are only possible, at least up to now, where this theory is treated in a harmonic way. And it's actually one of the open questions is how do you generalize this to nonlinear case? Okay, so then we're all familiar with dualizing standard bosons. So this guy dualizes to conventional U1 vector electromagnetism, where kinetic energy becomes E squared, and the density squared becomes the magnetic field. But then, of course, the defects in this theory, this is a compact theory, phi is compact, so it has also defects. The Goldstone modes of it are described by this electromagnetism, but the defects are encoded in this current J. That's the vortex current, which couples minimally to the vector potential, whose curl gives you the boson density and boson current. Okay, so then you look at and this is what these gentlemen did. You then look at this current. This current is just a curl. It measures the non-single valueness of the phase phi. So it's the curl of a grad of phi is the current. But then and so that's a very standard thing on the duality. But now if you look at a particular phi, namely phi that's, that's a profile phi that you get for the vortex lattice that I described in the previous transparency, then you get this Jacobian-like form for this current, which you can then expand around a uniform vortex lattice state. And that is what is going to give you a coupling between this electromagnetism, vector electromagnetism, and the elasticity. It's going to come in through this J dot mu. So the J, this J right here, can be written in terms of some lattice state plus the deviations encoded in the phonons. And so from that, an effective field theory of a vortex lattice, rotated superfluid vortex lattice emerges. So a vortex lattice is a Wigner crystal, which is this piece, but coupled to a superflow, which is encoded in this U1 vector electromagnetism, and where the couplings comes in through the J dot A. Yeah.
If you have some normal component accompanying your superfluid, what will be the difference in the theory?
Yeah,
Are there some effects?
That's complicated. Yeah, that's why I changed my title from EFT to QFT, zero temperature QFT. So yeah, I don't know what happens. Yeah, I don't want to speculate on my feet. Maybe Song has some commentary, but I think it's a complicated question, at least to me. Okay, but it's a very interesting question. Okay, so then you stick these guys into this coupling, and now you get this. So what you get is, so there's a coupling, and you can see here. I won't go through this, but once you stick it in here and you ignore the subdominant electric field square term, then you're able to exactly integrate over zero component of the gauge potential basically the scalar potential, and that imposes incompressibility on this crystal. And so lo and behold, so all that's left is the shear modulus piece of this general tensor. This is the b squared, e squared I've dropped as a subdominant piece. You encode this term gives you non-trivial non-commutativity between ux and uy components of the phonons, as you normally have for particles in the magnetic field. So this is the guiding center dynamics. But then there's this non-trivial coupling that comes from here that encodes how the superflow, which is contained in A, couples to the vortex lattice. Okay, so you can think of this as, if you integrate by parts here, dA dt is the electric field, and it dots into U. And so that's just nothing more than, well, so if you want to get, that's nothing more than actually superflow acting on vortices. And one way to kind of see that is to look at the equation of motion, and the equation of motion is given here, and it can be massaged into a Kelvin-like equation, which basically says that the motion of vortices, vortex velocity, vortices move with a velocity equal to the local superflow. So J is the local superflow, which is really contained in this electric field. The electric field represents the spatial component of the flow. And so if the right-hand side, if there are no stresses on the system, then vortex velocity just gets convected along the superflow, and that's the Kelvin condition. And if you have some forces, then that, this guy, the stresses on the system measure this difference. Okay, so yeah, so this contains the right physics, and this is the field theory that that describes a rotated superfluid, and the rest is sort of thinking about it at low energies and trying to extract more physics out of this, and maybe analyzing symmetries and looking at sort of generalized symmetries of this that are implicit in this model, but one can make explicit by dualizing and examining and looking also at topological defects, and in particular, maybe condensing those defects and melting this crystal. So from that, so this is the now the starting point of further discussion. Again, if there was no superflow, if you just had a Wigner crystal, then you could then that corresponds to gapping out the vector potential. Wouldn't be a superflow. You would just have elasticity plus the guiding center dynamics. For example, for particles in the magnetic field, like electrons. But you get incompressibility, so divergence of U, incompressibility harmonically encoded through the vanishing divergence of U, which is solved by this equation that many of you have seen, that the flow is actually perpendicular to the displacement. So if you displace, that corresponds to a flow, induces a flow that's transverse to the displacement. And sticking this guy into here just gives you this generalized Lifshitz equation with a Berry phase term. Typically, well, so so this is familiar, it's been discussed, and this is a Berry phase term that goes back to, really comes from this guiding center dynamics, non-commutativity of the components of the displacement field. And, so for single valued configurations of phi, this just vanishes due to the commutativity of the derivatives with this epsilon symbol. But once you have non-single value configurations of this phi, then this thing can be massaged into a form where you have vortex density coupled to d phi dt. And with some coefficient, and the coefficient is actually a ratio of boson density to the rotational density or flux density. And so this makes sense. This is actually just the PQ dot term, n dot d phi dot, where n is the number of bosons that have been depleted that are occupying a core of the vortex. That's how I interpret this, although it's not very precise given this gapless nature of this theory. So there's not I haven't found a strict argument for what this coefficient must be. but sort of at the dimensional analysis level or the sort of, this term makes sense, and we understand the physics, and it modifies modifies commutation relations, as I will discuss, that come out from this theory. Let's see what else I want to say about this. Yeah, maybe. Okay, but then, so one thing that emerges from this is the simplest way to get the Tkachenko modes that have been predicted going back to the 60s. There's a what emerges is a single polarization mode corresponding to this phi with this quadratic dispersion that's been mentioned before, and it's akin to a dispersion of a ferromagnet, where there also you have a single polarization. And the decay of this mode has been computed by Yi Shen and company, and is predicted to go as omega cubed. And as I understand, I haven't checked this calculation, as I understand this disagrees with the earlier predictions in the literature from the 60s. Yes?
Sorry if I missed it. What is big D?
What is what?
Big D.
Big D is a second derivative, traceless tensor, which is a second derivative, di dj minus 1/2 Laplacian delta ij.
Okay, thanks.
Yeah. It's just in this incompressible limit, that's what emerges. But more generally, just think of it as a second derivative. So it's encodes this quadratic dispersion. Yeah.
Should we require this prefactor of the Berry phase quantize? Because I think that the formalism looks like a topological term, something like.
Well, it is a Berry phase term, much like it's not topological, but it's a Berry phase term. Yeah. It encodes how flow interacts with vortices.
Should we require the prefactor quantize?
No.
No.
Particularly in this compressible system, it's not. As far as I understand, there's no argument for why it has to be quantized. Speaks to my comments about this. That there's nothing that's quantized about it. I don't know if you.
I should have no argument that the coefficient should be exactly.
Right, I don't have an argument. Maybe you do, but
I don't have an argument.
Okay. I mean, even in the context of ordinary superfluids, non-rotated ones, there's a beautiful paper by Haldane where and the arguments between him and Stalos discussing this, and conclusion is because it's compressible, there's nothing that encodes the quantization of that coefficient.
But does this coefficient the same come from the coupling of the emergent gauge field with the lattice? So you can go back to the coupling of the
So here the coefficient is certainly 1.
And then from this you can do integral by part, and you see that the A mu back to this term.
No. Okay, certainly when I do these manipulations, and when you guys do these manipulations, you get a particular coefficient. Here it is, and then here it is. So, I preserve the coefficient. The question is the coefficient something robust, or is it just artifact of these manipulations? So that's really the question. Like, is there a Laughlin-like argument or something that tells you what the coefficient is? Like, if you weren't deriving it and just wrote it down, can you say what it is? Okay, and so then we developed this. There's this dictionary between elastic degrees of freedom and the gauge vector electric and magnetic fields and the corresponding operators in the Lifshitz model. Okay, so what if you're bored? You have this model, you could be happy with it, but maybe you're bored and you like dualities. So one thing you could do is dualize it, and that's become quite fashionable. So if you do this, then this guy maps onto the traceless tensor gauge theory, where the gauge fields are Aij, and there's a zeroth component, and the corresponding electric field, electric symmetric traceless electric field, and a scalar magnetic field, and the Lagrangian looks like this. So it's E squared plus B squared, but B squared is coupled to the divergence of U in this minimal way. And then there's this still this Berry phase-like term. Notice it turns out that this U that appears has nothing, well, it looks like a displacement, but it's not, and for that reason I'm using the same letter, but it's not the original displacement. It's a Hubbard-Satonovich field that emerges when you dualize this guy. But ultimately, its physical interpretation is the original phonon of the original theory, but now coupled to this tensor magnetism, electromagnetism. And so here's the dictionary between d phi dt and the magnetic field, this shift of magnetic field, and this d phi in the electric field, certain components of the electric field. There's also an alternative way of doing this, doing the original, fracton elasticity duality on the original, not on the Lifshitz model, but on the original elasticity model, namely, on this model. And if you do that, you get a tensor gauge theory that's not traceless, but at low energies, it can be shown to reduce to this theory. So then one can examine symmetries. So in the crystal description, there's a U1 symmetry of atom conservation, boson conservation, corresponding currents. That corresponds to standard charge conservation. And then there's translations and rotations that have standard descriptions. In all of this, on the Lifshitz side, gets collected into this multipolar symmetry where there's a, quadrupole is the highest multipole that's conserved. That corresponds to angular momentum conservation. And dipole corresponds to translations, and this guy corresponds to a charge conservation. So you get this dictionary where all of this charge conservation, linear momentum, angular momentum just collects into this non-trivial tensor-like current, Jij, with its corresponding time component. And then it looks like this multipole, quadrupolar symmetry, quadrupolar, dipole, and monopole symmetry. And then there's corresponding algebra of the operators of the fields. So with this, one can then look at topological defects, and that's just recognizing that this phi field of the Lifshitz model is a compact field, so it has these non-trivial identification under 2 pi rotation, and so certain derivatives of that phi field, for example, Laplacian corresponds to the angle, orientational angle of the of this symmetric-like state or crystal, and defects in that, namely vortices in that, curl of a grad of theta, correspond to disclinations, and proliferation of those restores rotational symmetry, but also U1 symmetry. And this is the profile of that disclination. There's also line-on operators, which can be expressed in terms of the particular configuration, singular configuration of phi that costs logarithmic energy. And then there are mobile, and this is a line-on, and then there's mobile vacancy interstitial configurations, which are just nothing more than the vortices of this phi. Notice this phi is a new field that appeared, which solves this incompressibility constraint, but it actually looks like a superfluid phase. And in fact, its curl describes additional vortices you've added on top of your vortex lattice, so that's the vacancies and interstitials. Okay, so that's the addition. The vortices in this phi are the extra deviations. It kind of it acts like a right-hand side to the divergence of U. So here's the dictionary for those defects. Then one can look at defects in the winding, one-form symmetry defects. These are the ones that appear, that look like one-form symmetry in this tensor gauge theory description. And they appear as the time-like defects, Wilson loops. So for example, the fracton monopole or vortex disclination looks like the conventional Wilson loop, just in a time direction. And there's no spatial component because this guy has no current. It's reflective of the fact that it's a fracton. There's a line-on form of it, which is again expressed in terms of this time component of this tensor gauge theory, a gradient of it with the dislocation charge appearing in the coefficient. And finally, there's the mobile quadrupoles are created by this Wilson operator. And so this is the summary of these operators with the dictionary. So I'm running a little bit over, but so let me just take 2 more minutes and talk about melting. So now we understand the defects, we understand the theory, sort of the continuous part, and we understand the defect part, and now we want to put it together. So this is, again, for me, going down the memory lane. So in the 90s, we were all obsessed about phase diagram, magnetic field temperature phase diagram of type 2 superconductors, because the high temperature superconductors were discovered. Half of maybe 90% of the condensed matter people were focused on microscopic mechanism, but the 10% maybe of us who were focused on sort of effective field theory and the sort of phenomenology of vortex matter. So it kind of opened up this whole field of line crystals and line matter, vortex line matter. And so, it's a conventional picture going back to Abrikosov, you have this vortex lattice. It's fairly boring. It doesn't do anything. It just sits there because it's effectively at 0 temperature. Fluctuations are very weak. But then it was recognized that in this high temperature superconductor context, vortices become a matter, like a mesomatter itself. So now one can talk about crystals of that matter, but that matter can melt into a liquid. And this is this beautiful seminal paper by Nelson and Song, 1989, that recognized this and discussed this kind of a transition. It's genetically a first-order transition. But then with Cristina Marchetti in 1999, we start thinking about intermediate phases of this, this first-order, generically first-order transition. And so we had to think about dislocation loops. So now think about 3-dimensional classical lines. So you have classical vortex lines. So then the defects are also loops. And so you can think of a dislocation loop. Here it is. You can either glide by making the loop stretching or shrinking in this way. But also there's a potential climb. But it turns out, and this is the aforementioned glide constraint, that it was originally thought that this guy has to be 0. And indeed, it's 0 if there are no vacancy interstitial defects. You have a perfect crystal, commensurate crystal. But in fact, this is what this condition becomes. And it allows, what it does is vacancy interstitial allow for this dislocation loop to tilt out of its own plane. And from that, we predicted a phase diagram that's, rather than having a first-order transition, which is what Nelson and Song talked about over here, there are these potentially intermediate phases that are allowed. So now if you think about these guys as world lines of 2-dimensional bosons, then so then you can think of it as a 0 temperature quantum version of these transitions. And so you get a vortex supersolid where vacancies proliferate, vortex exotic or smectic, depending on which dislocations proliferate, and then a vortex liquid that the vortex crystal can melt into. And in this dual description, these just look like Higgs transitions of this Lifshitz gauge theory. So this is how it is. So you take this electromagnetism with this Berry phase term and just couple it to matter. The matter is describing dislocations or disclinations of vacancies. Well, in particular, vacancies interstitials, as I've written it here. So this is the effective vector potential, scalar potential for the representing vacancies. And when you proliferate those, this guy undergoes a Higgs transition. Then this traceless gauge theory becomes a traceful tensor gauge theory in the vortex supersolid state. And then now dislocations are allowed to climb, and that's corresponds to modification of the Wilson loop operator. Okay, so with this, I'm just gonna put up the summary, and thank you for your attention.
Hi. Yeah, thanks a lot. It was great. So do you have interpretation of the coupling of this divergence of U to the dual magnetic field? So, like, do you have an intuition for that? So,
let me pass on that, but you know, it encodes the fact that it's you know, compressing the lattice and which is this divergence of U, and this magnetic field is not independent degrees of freedom. It's really just they're representing the same physics, but we can maybe discuss afterwards, but I
right.
could say a few more words about it.
okay, thanks.
Yeah.
So I have a question about symmetries. You didn't mention anything about boosts. Do you have any like
About what?
about boosts, like Galilean boosts in your theory? Do you assume anything about it, or it's just like hidden somewhere?
I think once you go to this harmonic approximation, I think it's you break that symmetry. I don't think you have Galilean invariance at this harmonic level. So I think in order to really have full Galilean invariance, you need to go to nonlinear order.
Then you have a question. Okay, now let's hang the speaker again.